Let's look at how to differentiate inverse trigonometric functions. Now, what are the examples of inverse trigonometric functions? Functions such as inverse sine x or inverse cosine of x or inverse tangent of x, inverse cotangent of x, and so on. So let's try to differentiate inverse sine of x. First, we write x in terms of y and it will become simply sine of y. Now we can differentiate dx dy, and that is simply cosine of y. In terms of x, what is cosine of y? Now we can figure that out from trigonometric identity. We know that sine squared y plus cosine squared y equals to 1. That means cosine of y in terms of x is quite simply 1 minus x squared, square root. And the last step is to use the rule that dx dy is quite simply 1 over dy dx. So inverting this result, we get dy dx equals 1 over square root 1 minus x squared. And that's the result of differentiating y with respect to x. What about the following function? Arctangent of x or inverse tangent of x. So again, you use the same trick. You express x in terms of y and that becomes tangent y. This we know how to differentiate. When we differentiate x with respect to y, it is simply secant squared y. Now let's look at one of the trigonometric identities that says tangent squared x plus 1 equals secant squared of x. Of course, this identity is true for x, for y, for any variable. So I'm going to rewrite secant squared in terms of tangent squared, and it will simply become tangent squared y plus 1. Now simply replace tangent y with x, and you get x squared plus 1. Since we are interested in dy dx, because y is that, and remembering dy dx is 1 over dx dy, which we have already found, we get dy dx to be 1 over x squared plus 1. And that's the answer. The result of differentiating y with respect to x when y is given by that function. Now let's look at how to differentiate inverse cotangent of x. So playing the same rule, first by expressing x in terms of y, we get cotangent y. So let's try to differentiate x with respect to y here, when x equals the cotangent y. Now cotangent is cosine y over sine y. Now if you use quotient rule, you differentiate the top, you get minus sine y, multiply that with the denominator, sine y, subtract, differentiate now the denominator, you get cosine y, multiply with numerator, cosine y, over the square of the denominator, sine y squared. So minus sine squared minus cosine squared is just minus 1 over sine squared y, and you get minus cosecant squared y. So let's write the result here. Let's look at trigonometric identity. We know that sine squared of theta plus cosine squared of theta equals to 1. If you divide this entire equation, let's say by sine, you get 1 plus cotangent squared theta equals cosecant squared theta. So using this identity in here, you see that minus cosecant squared is minus 1 minus cotangent squared y. Now we know what is cotangent y in terms of x. That is quite simply minus 1 minus x squared. So dy dx, which is 1 over dx dy, is quite simply minus 1 over 1 plus x squared. And that's the result of differentiating y in terms of x when y is defined by inverse cotangent of x. Now let's look at this function. Note, it is a inverse cosine, but x, the variable, appears below, and a is a constant. But you play the same trick. First, express x in terms of y, so a over x is cosine of y. That means x over a is secant of y, and x is a secant of y. A secant of y is quite simply a over cosine of y. Now let's differentiate dx dy using quotient rule. Differentiating a, you get 0 because it's a constant. You multiply with cosine y, subtract. Now you differentiate cosine y, you get minus sine y. Multiply that with the numerator, which is a. Divide by the square of the denominator, which is cosine y, and square of that. So the final answer is, for dx dy, is a sine y over cosine square y. Note, from this line using trigonometric identity, we know that sine of y is 1 minus cosine squared y square root. So square root 1 minus a over x squared. Substituting this result and this result in here, we get dx dy is quite simply a sine y is square root 1 minus a over x squared, divide by cosine squared. So that means x over a squared. Simplifying, we get a square root. Let's bring x over a squared inside the square root sign, and you're going to have x over a power 4 minus x over a squared, which can be simplified using algebra, and it will become x over a square root x squared minus a squared. What we are interested in is dy dx, and that is 1 over dx dy. We already know what dx dy is, and that is that. So that means taking the inverse of that is quite simply a over x square root x squared minus a squared. And this is the answer for the differentiation of y with respect to x, and y is given by that function. Let's look at this function, where the argument of sine or arcsine is square root of x. Same technique, you express x in terms of y, so it becomes sine of y, or x is sine squared y. Now let's calculate dx dy. It is quite simply, you bring the 2 in here, 2 sine y, and then differentiate just the sine y, you get cosine y. Sine y is square root x. What about cosine y? Now cosine y is square root of 1 minus sine squared y. So that means it's 1 minus x. So substituting everything inside, you get 2 square root of x, square root of 1 minus x, or 2 square root of x minus x squared. Finally, we know dy dx is quite simply 1 over dx dy. Since we know what dx dy is, 1 over 2 x minus x squared will give you the required answer. Let's look at this example. Y is inverse of sine x and square the whole thing. So expressing x in terms of y, you get sine of square root y. So dx dy need to be determined first. Now we can use differentiating function of a function to get dx dy. If we assume that g is square root of y, then dx dy is dx dg dg dy, where x is now can be expressed in terms of g as quite simply sine of g. So dx dg is just cosine of g, and dg dy from here is 1 over 2 square root y. So there we have it. dx dy is 1 over 2 square root y times cosine of g, where g is square root y. So let's write this result entirely in terms of x. Square root y would quite simply be inverse sine of x. So 1 over 2 inverse sine of x, because y is the square of inverse sine of x. So square root y is inverse sine of x. Cosine of inverse sine of x. Again, by using the fact that dy dx is 1 over dx dy, we see that dy dx is 2 inverse sine of x over cosine inverse sine of x. And this is the answer that we are looking for, namely the result that you would get by differentiating this y with respect to x. Let's see if you can simplify this further. Now the denominator is cosine of arcsine of x, and this is quite simply square root 1 minus sine of arcsine of x squared. Using trigonometry identity, we are simply using cosine of theta equals 1 minus sine squared theta, where theta is this entire thing. Sine of arcsine of x is quite simply x. So that means this result right there, the dy dx, where y is given by this function, will simply become 2 arcsine of x over square root of 1 minus x squared. Don't forget the square there. And this is the final answer for the differentiation of that function with respect to x. Thank you for watching.